Hello, and welcome to the chapter 15.4 lecture on the chain rule. So recall from single variable calculus that if f is a function of x, where x is a function of t, so a composite function, then df dt is df dx times dx dt. And one way to think about this is that the dx's cancel out, leaving your df dt. But what if f is a function of two variables, f of x and y, each of which is a function of t? Well, here's the theorem. Given a function f of x, y, in which x and y are functions of t, then df dt is df dx dx dt plus df dy dy dt. And why is this? How can we visualize this? Why does this make sense? Well, df dx, del f del x, this is the rise of f per change in x, and this guy is the change in x. And that means that this product in total will be the rise of f in the x direction. So in other words, this rise, if our change in x is this. And similarly, this guy will be the rise of f in the y direction. So it would be this guy. And if we add those together, then through vector addition, we'll end up with a total rise per delta t of the vector sum. So imagine adding the green and yellow together. And that will be our total rise in f as t varies. And remember that as t varies, both our x and y are varying. And each of those contributes an amount to the total rise in z. And that is by this planar linear approximation in essence. We'll get into planar linear approximations more in a bit, but this is a great way of visualizing it for now. So let's do an example. And I'm going to do this example in two ways. First via a direct substitution, and then we'll do it with the chain rule. So first with the direct substitution, that means that we would just first substitute x equals t squared and y equals t cubed into f originally. And that means that f of x, y is now f of t is sine of t squared squared times t cubed. And that is sine of t to the 7. And then df dt is the derivative of sine t squared is 7t to the 6 cosine of t to the 7 by the single variable calculus chain rule. And yes, that isn't bad at all. But now for the sake of illustration, let's apply this. So applying that, we have that df dt is del x of sine x squared y squared, that's our f, times dx dt, that is d dt of t squared since x is t squared, plus our del f del y times d dt of y, which is t cubed. So putting it into this looks like that. And now we compute those partial derivatives and the single derivatives, and we get this. And you can verify that this is indeed the partial derivative with respect to x of that, and so forth by the single variable chain rule. Okay, now, this doesn't look like we got before, does it? And that's because what we got before was in terms of t only, while this has x's and y's in it. So to get this in terms of t only, then we would do a substitution with x is t squared, y is t cubed, and then we get this. And now simplifying that, we get this for each of those terms. And then adding those together, we get our 7t to the 6 cosine of t to the 7, which is the same thing that we got before. So clearly in this case, this method is longer, but I wanted to illustrate the method and how it's the same as what we get with direct substitution. And in other cases, this method will be quicker, especially if we can't do a direct substitution, which might happen sometimes. So go ahead and try your hand at this using the multivariate chain rule rather than direct substitution. Okay, and we get this substituting, and then computing those, we get this. And now if we want to substitute x is sine t and y is cosine t, then we get this. And we can simplify that a bit more if we want to this. And if you want, you can do the direct substitution and verify by the single variable product rule, in this case, that you would get the same thing. Now, this was the chain rule for f of x and y, where x and y are both functions of t, but we can extend it to functions of more than two variables. And it's what you might expect. If you erase this part, then it looks like the chain rule that we already learned. So we add in that third term for the z part. And in general, we can think of it with this diagram, and this kind of diagram we can use to generate chain rules for more complicated situations. And the way that this diagram works is as follows. So we have our function w. W in this case is our f, and f is a function of x, y, and z, and each of x, y, and z is a function of t. And the way that it works is each branch, like this blue branch, that would correspond to this. And as we go down a branch, then we take the product. So del w del x times del x del t is this. And we also have this branch, and going down that branch and taking the product of those two, we get this term. So we take the product along branches and add together the different branches. And lastly, this branch, that product is this guy, and we add it together. So product along branches, then add the branches together. And that can generate chain rules. And this works in general. And the only caveat is that if your end function is a function of two variables, then to generate the chain rule, you would look only at the branches ending in that variable. So if z is a function of x and y are each functions of s and t, then if we want to find del z del s, then that means that we would look only at the branches ending in s, which are denoted in this diagram as the red branches. So this branch here is that del z del x times del x del z. And then we add it to this branch, which is del z del y times del y del s. And if we wanted the derivative with respect to t, then we would look only at the branches ending in t and do the same thing. This branch is that, and this branch is that. On some homework problems, it asks you to generate chain rules for a situation, and this is how you do it. You draw the tree diagram, and then you go down the branches ending in the variable with respect to which you want to take the derivative or partial derivative, and add those branches together. So suppose f is a function of x, y, and z, each of which is a function of s and t. Find the chain rule formula for del f del t. So we would begin by drawing our tree. Our highest function is f. F is a function of x, y, and z. So there's x, y, and z. And each of these guys is a function of s and t. And each of these edges corresponds to a derivative or a partial derivative. So for example, this guy would be del f del x. This guy is del f del y. This guy is del f del z. This one would be del x del s, etc. This guy would be del z del t. And now we look at the branches ending in t in this case. So that'd be the branches ending in these three t's. And we go down the different paths that end in t. So here we would have that del f del t is del f del x times del x del t is that first branch. The second branch is that guy ending in t. So that's del f del y del t. And the last branch, this guy, is del f del z del t. So that'd be our chain rule for this situation. Okay, go ahead and try your hand at this. Okay, so our tree diagram looks like this. And what we want is the branches ending in t. In this case, that's all of the branches. So we go down each of the paths and generate our chain rule. Now, is this going to be del f del t? No, because that notation is used for partial derivatives, as if f would be a function of t and multiple other variables. Here, because all branches end in t, f at this level is a function of t only, so this would be df dt. So be careful with that notational distinction. Okay, and the branches are these. And note that some of these branches partially overlap. That's no problem. So we have our del f del x times del x del u times du dt. Notice again that notational distinction. That's because u is a function of t only. So that is a single variable derivative. It's not a del u del t. These first two guys are partial derivatives, though, because f is a function of two variables and x is a function of two variables. Likewise, then this yellow branch is this, green branch is that, and purple branch is that. So this is our multivariate chain rule for this situation. Yet another example. W is a function of z, z is a function of x and y, each of which is a function of t. So the tree diagram here looks like this. In this example, I didn't write the labels of what the branches are, but as you know now, each branch component is just the derivative or partial derivative going from that node to that node. So this would be del z del x. And we want dw dt. Each of these ends in t. So this will be the product of these two, of the guys along each branch, summed together. And that is this. Again, notice the notational distinction. Whenever we have a function of only one variable, that's a single variable derivative, dt, whatever, while z is a function of two variables, that's the partial derivative in the middle. Now, implicit differentiation. We'll be doing implicit differentiation with multivariate functions naturally, but first let's review what implicit differentiation is in the Calculus 1 context. So I'll do this with an example. Let w of z be the function implicitly defined by w times e to the w equals z. It is impossible to solve for w in terms of z in this function in terms of elementary functions. And this function happens to be called the Lambert W function, but we don't need to know that. So despite it being impossible to solve for w in terms of z, we can still find dw dz, possibly in terms of w and z, by implicitly differentiating both sides. So we have d dz of w e to the w is d dz of z. So that's taking d dz of both sides of this. Now, this right-hand side, d dz of z, is just 1. Derivative of z with respect to z is 1. And the left-hand side, this is not 0. This is not a partial derivative where we're imagining w is constant with respect to z, because w is not constant with respect to z. As z varies in this equation, so does w. W is an implicit function of z, and this is like f times g. And we know that the derivative of f times g is f prime g plus f g prime by the product rule. So in this case, that's w prime times e to the w plus w times e times w prime times e to the w. And this guy, that's because w is a function of z, so by the chain rule, it's multiplied by the derivative of the inside. Now, to get w prime, we want to solve for it in this equation. This is the same as w prime times e to the w plus we to the w is 1. And thus, w prime is 1 over e to the w plus we to the w, or we can rewrite that if we want as 1 over 1 plus w times e to the w. Now, we want to extend this to implicit differentiation in multiple variables, and I'll illustrate this by example, and then it will work in general. So the way that we do this is we take our function, in this case w to the w is z, and rearrange it so that the right-hand side is 0. And then we think of it as the level curve of a higher dimensional function. So we imagine this left-hand side, we to the w minus z, as a function of w and z. And then a level curve of this would be setting this guy equal to 0, setting the output equal to 0. Technically, yeah, so that's the level curve for that. And now we take the derivative of both sides with respect to z, except now this left side is a function of 2 variables, so that's a partial derivative. So, and derivative of 0 is 0. So we have that del f del z is 0. And now this guy, f is a function of w and z, each of which is a function of z. So by the multivariate chain rule, it's this. Now, dz dz, we can think of that as d dz of z, and that is 1. So this guy goes away. And it was kind of weird to see it dz dz, but this is all it means. So that's the same as multiplying by 1. So we just don't write it. And what we were interested in was dw dz. So now we solve for dw dz by moving this to the other side, dividing both sides by del f del w, and we get this. Or using our alternate notation, del f del z, our alternate notation for the same thing as f sub z. Likewise here. And this process works in general. Notice that in this derivation here, we did not use the specifics of this function whatsoever. This formula will just always hold true. Okay, and here we use the variable names w and z. If we use the variable names x and y instead, then it becomes this formula, exactly the same thing as what we just derived. So that's our theorem on implicit differentiation. If f is a differentiable function, and we move everything to the left-hand side so that it's equal to 0, and we regard that whole left-hand side as a function of x and y, then dy dx is negative f sub x over f sub y. Okay, let's redo this implicit differentiation that we did using Calc 1, now using this formula to illustrate it. So we know that dw dz is negative f sub z, that's del z of w e to the w minus z, over f sub w, that's del w of w e to the w minus z. And now these are proper partial derivatives. And this is -1, because now w is constant with respect to z in this new way of thinking about it, over this. Z is constant with respect to w, so the derivative there is 0. And for w to the w, we use the product rule. And that is e to the w plus w e to the w. And that is 1 over 1 plus w e to the w, which is the same thing that we got before using the calc 1 method. Okay, that concludes 15.4. Have a great one.